Yes, hi everyone. Good morning. All right, let us continue our discussion on the in Google Drive, machine learning Excel sheet is missing. Is it? Yeah, it's not there. Correct. I don't know what has happened. I did not give any permission to there. Only viewer permission is there, no? Mm, mm, mm. Okay, let me just check. Okay. Not there. Nobody has downloaded that. That is a big problem. I have not done anything to that. Even I don't know who has done it. Yeah, okay, okay, okay. Hmm. Hmm. Might be that too. What should be done? I'm not doing anything, guys. ठीक है, नो इश्यूज, नो इश्यूज। I know, name was machine learning, but it's not there now.
Hey guys, welcome to Research Rock. Very simple one of my Google Drive. After that, here my Google Drive storage almost full. So I just simply delete this one, Shadi ki anniversary, this folder. Get this, click and remove. Even I go back hash. Again, I
Want this?
and here several link is coming here. You just simply click here, delete and restore file on Google Drive. Here several different options are available, computer, Android and iPhone. You can restore very easily. Some step-by-step process is going on. If you delete the data, you can restore via hash. If you delete the data via hash, so this video is very important for you. You just simply scroll down here entire the bottom of the screen. If you need to recover email from Gmail and recover request here, you just simply click here. After that, you select your email address, which email address drive you are using. And here recovery file related options are coming. You just put it here, your first name, last 25 days, yes. And here which types of data you want recover. So you can select your option and
Google Photos, okay, Gmail, WhatsApp can't be recovered. ठीक है. Learn how to recover emails. चलिए file recovery, request file recovery. पास की हूँ. Can't do anything, guys. Somebody must have downloaded that. Nobody downloaded that offline. You people should have downloaded that, no? Nobody downloaded that. Okay, no issues. Let's not focus on that. Okay, let's go to this. Let's go to this. Right. Now, in the last session, discussed we have discussed about where is that? Day 38. I don't have any file here. Day 37. Ah, okay. We have discussed about convolutional neural networks and its libraries, right? How to read image, correct? Then we have discussed how do we change color of the image, correct? Then we have discussed hmm, then we have discussed um, how to change color, black and white, something like that. Correct. Now it's time to discuss the next part. That is your, what was the next part? That is your pooling layer, right? Let us discuss that. Oh, this is what we have, no? This file, guys. This one only, correct? Yes or no, guys? It is recovered. Can you see it? Nice. You must download this now. I am also downloading it. You must download it, guys. Nice. I can't see this in your drive. Okay. Your drive it will not be there, no? Here it will be there. If it is not there, just let me know. I'll upload it one more time. Okay, I'm uploading it now. You can see it, right? Keep both files. I'll just keep both files. Getting it, guys? Now can you see it? Machine learning 1. Correct? Just download it, guys. Quickly download that. I think I was removing this thing, no? I was clearing the storage. Unknowingly, I did that. Matlab, not purposefully. I was clearing this thing. So that's the reason it happened. But ठीक है. No issues. Okay, so last session we have discussed convolution, we have discussed padding, notation, why padding is necessary, we have discussed important formulas, weights of CNN, comprehension weights and biases, right? Correct? Now, now we should see a new thing, that is your feature maps. Let me just zoom it a little bit. Okay, let me just create a new shade. Let me just 20-second wait. Let's call it as feature maps. Correct? Okay. Now from the previous segment, you know that the values of the filters or weights are learned during training. Weights, values, or rather weights and filters are learned during specifically back propagation. Right? Back propagation. Let's now understand how multiple filters are used to detect various features in image. How multiple filters are used to detect various features in images, right? So in this session, you will study neurons and feature maps. So what is a neuron, guys? It's a basically filter whose a filter whose weights are learned during training. For example, a 3 cross 3 cross 3 filter or neuron has 27 weights, and each neuron looks at a particular region in input, that is its receptive field. Correct? Then what is a feature map? It's a collection of multiple neurons, each of which looks at different regions of the input with the same weights. And all neurons in feature maps, all neurons in feature map extracts the same feature, extract the same feature, but from different regions of the input, right? So a feature map is a collection of multiple neurons, each of which looks at different region of the input with the same weight. All neurons in the feature map extract the same feature, but from different regions of the input, right? It is called feature map. It is called feature map because it is a mapping of where a certain feature is found in the image. It's called feature map because it is mapping of where a certain feature is found in the image. So if you see feature maps in CNN, you'll get an idea about that. Let's watch one video quickly. Short video of 2-3 minutes. Oh, sorry, I have not shared that sound. Just a minute. Sound. Mhm. Now, hmm.
In the previous video, we trained a filters about that, like a 5x5. See that you can, the list, it has two items, right? So I'm iterating through these, this whole thing is, so is this other, of child, sorry, of layer, this will have those feature maps, but don't rush. Again, this is the nice. This is very convolutional layer. That is why, yes, before I printed for loop that would go through
It's just a coding
labels
line.
and okay, so that's the idea. Here we've got all of the feature maps, and you can see that there are some very nice patterns. Some
Feature maps and see. It's nothing but if I get an image, this is my image. Can you see this, guys? This is your filter, right? You're putting that into your image, and what you are getting is output. That is a feature map, correct? So, for example, in early layers of CNN, feature maps may represent low-level features such as edges, lines, and corners, right? So, what happens is, if you just do in the first level itself, as you can see in that video as well, first we are getting very low-level images, low-level features, that is edges, lines, and corner. If you are moving with the deeper neural network into the network, feature maps may represent more complex features such as shapes, textures, and even the whole objects, right? So, this is your syntax, or this is your sequence in which you are getting the feature map. If you read this thing, you'll understand how. So feature map is the output of the convolution layer representing the specific features of the input image, right? As you are doing convolution operation, you are going to achieve some features, no? So that is mapping of that feature is known as feature map. During this forward pass of CNN, input images convolve with one or more filters to produce multiple features map, and each feature map correspond to a specific filter and represent the response of the filter to that input image. Each element in the feature map represents the activation of a specific neuron in the network, and its value represents the degree to which the corresponding feature map present in the image, right? For example, we have discussed this. In early layers, feature maps may represent low-level features. As as we move deeper into the network, the feature map may represent more complex features such as shapes, textures, or even whole objects. Right? Now, the number of feature maps in a convolution layer is a hyperparameter that can be tuned during the network design. And increasing the number of feature maps can help the network learn more complex and abstract features, but it also increases the computational cost and may lead to overfitting if the network is too large, right? So increasing the number of feature maps can help the network to learn more complex and abstract features, but it can also increase your computational cost associated with computations, and it may lead to overfitting of the network and becomes too large. So after each convolution layer, nonlinear activation functions such as a ReLU are typically applied to introduce nonlinearity to the feature maps. Then pooling layer, we have not seen this pooling layer. We'll see that used to reduce the spatial size of the feature maps while preserving the most important information, right? An example of feature map is this. You are applying this filter. Here, this is your image. This is going to be a feature map, right? Now different filters and feature maps. We have seen this. You can read this article. So what are the different pros? Feature maps can help extract and highlight important information features in the image, which can improve accuracy of the CNN in tasks such as image recognition, object detection, and speech recognition. Your feature maps can help to reduce dimensionality of the data, making it easier and faster to process and analyze. By using multiple layers of feature maps, a CNN can capture complex and hierarchical relationships between different features in the input data, leading to more accurate and robust predictions. Feature maps learned from one task or dataset can often be transferred to another task or dataset, allowing the CNN to leverage knowledge gained from previous tasks or datasets. And this can lead to faster training and improved performance on new tasks or datasets. What are the different cons that we have? It is computationally expensive to compute, especially when using large input image and multiple layers of feature maps. CNN can typically have a large number of parameters or and require a significant amount of memory to store and process the data. The size of feature maps can also become very large, which can be a challenging to handle in terms of memory requirements. Feature maps can sometimes be overfit to specific features in the training data, leading to a poor generalizable generalization and performance of unseen data. And the quality and interpretability of feature maps can be affected by using a choice of architecture, your hyperparameters in the network, and the training method that you're going to use. I think this is more than enough for you. So I'll quickly take this. Let me call paste it over here. You can read about this for the feature map, right? Now, that's what I wanted to show you. This is your diagram of feature map. You can just look at this diagram. You'll get a clear understanding of feature maps in the 3 dimension, right? So if you have 3 dimension, so there will be 3 dimension filter as well, and there will be 3 dimension feature map for each filter, right? Now, let me just give you guys a quick comprehension on feature map so that understand it. Feature maps. Now, consider a VGG net architecture. The first convolution layer, VGG net, huh? I'm talking about VGG net. Let me take VGG net. Right, this is your image. So the first convolutional layers takes the input image of size 224 by 224, and this 224 by 224 output is then fed to a ReLU to generate a 224 by 224 picture map. So note that the term feature map refers to the non-linear output of the activation function and not what goes into the activation function, right? So it refers to the nonlinear output of the activation function and not what goes into the activation function. That is the output of the convolution. Correct. Similarly, multiple other feature maps, multiple other, that is 224 by 224 feature maps are generated using different, let us see, by 3 by 3 filters. And in case of VGGNet, 64 picture maps of size 224 by 224 are generated, which are denoted in the figure below as the tensor. Here you can see, now it's not clear. This one is clear, so let's take this. right? So 224 by 224 by 3. So in case of VGG net, 64 feature maps of size 224 by 224 are generated, which are denoted in the figure below, as the tensor 224 by 224 by 64, na? 64. And each of the 64 feature maps try to identify certain features from the image, such as edges, textures, etc. in the 224 by 224, 3 input image. Right? Now, the 224 by 224 by 64 tensor is the output of the first convolutional layer, and in other words, the first convolutional layer consists of 64 3 by 3 by 3 filters, and hence contains 64 by 27 trainable weights, assuming there are no biases, right? So the 64 feature maps, or the 224 by 224 by 64 tensor, is then fed to a pooling layer. You will study the pooling layer in the next segment. Right? So these 64 feature maps, or 224 by 224 by 64, isn't fed to a pooling layer. Why pooling layer? We'll see that in the next segment. That is what we are going to discuss. Right? So now it's time to understand pooling. Now, what is pooling? Why it is required? We'll see that. But before that, to give you guys a more clarity, there's one video by a kid, I think, Convolutional Neural Network. He has explained in very simple word. His age is very less, and he has explained in very simple word. So, uh, this guy, this one, right? So, if you watch the series of this Convolutional Neural Network, you'll understand it very clearly, like what is happening, right? I personally have watched this multiple times, and I felt it is very, for the for those guys who are learning it for the first time, you should give it a try. Convolution neural network. This 12 videos, very easy,
Computer.
right? Just give it a try. This one. Okay. Now let us go back to pooling. So in our earlier discussion of the experiments, we have observed the following, that the strength, right? Strength of the response of what? Of the retinal neurons. That research paper which we have discussed, right? Very first session. So strength of the response of the retinal neurons is proportional to the summation over the excitatory region, right? After extracting features, as feature maps, CNNs typically aggregate these features using the pooling layer. CNN typically aggregate these features using the pooling layer. Let's see how the pooling layer works and how it is useful in extracting what? Higher level features. Correct? So uh let's watch this. Let's watch this pooling.
In previous videos, we learned how convolution operation works. We saw that the convolution operation is able to detect the features from the images. Now in this video, we will understand another powerful operation which is called max pooling operation, or in a convolutional neural network, this layer is called as a max pooling layer. Now, there can be many types of pooling layers in CNN, and the function of the pooling layers is to reduce the size or the dimension of the image while preserving the features in it. For example, this is the output after performing the max pooling operation on this input image. And in this video, we will understand how max pooling works, why do we use it, where do we use it, and we will see the power of using max pooling layer in our convolutional neural network. Also, if you have been following my content for a while, then make sure to hit the red subscribe button and follow my entire convolutional neural network playlist. You will find its link down in the description box. And for now, let's see what is max pooling. Now for performing the max pooling operation, we need to fix a filter of a particular size and a stride of particular amount. This filter can be of any size and you can take any amount of stride as well. But usually the amount of stride is taken as same as the side length of the filter. For example, here I've taken the filter size of 2 cross 2 and the stride as 2. Thus the output after performing the pooling operation will be an image of size 2 cross 2. And for performing the max pooling operation, what we will do is that we will place our filter at the top left corner. Then we will extract the maximum value of this window. And for this window, it is 8. So we will place 8 at this position. Then we will slide our filter or window by stride amount, which was 2 in our case. So we have moved 2 pixels to the right. And we will again extract the maximum value, which is 6 in this case. And as we have reached at the right edge of this image, we will move 2 pixels down and again extract the maximum value and put it at this position, and we'll perform the similar operation for this window and we will place 9 at this position. So this is how the max pooling operation is performed. Now let us see why we might want to do this. The first reason for doing or performing the max pooling operation or using the max pooling layer is that it reduces the image size. And reducing the image size means reducing the computational cost and thus getting the output faster or training the model faster. And we do want to make our operations fast, because let's say if we are making a mobile app in which we want to take the picture of any object and recognize the object in an image, and for that we don't want to wait too long while our CNN or convolutional neural network is performing the computation to identify the object in an image. So reducing the computational cost or reducing the size of the image reduces the computational cost and thus getting the faster output. And even though it reduces the size of the image, it still preserves the features of that image. And max pooling works in such a way that you can say that it actually sharpens the features or enhances the features. For example, if we take this image as an input and perform a max pooling operation, then we will get the image on the right as our output. You can see that there is a presence of a vertical edge in the input image, and this vertical edge is still preserved but actually even enhanced in the output image. In one window of an image, we can say that the maximum value will be holding the maximum intensity of that feature. So when we are extracting the maximum value, it is sharpening our features or enhancing our features. If we take another example, The image on the left is the output after performing the convolution operation using a vertical edge detection filter. And this output from the convolution layer or the convolution operation is when passed to a max pooling operation, we get an image on the right. On the right, you can see that all the features are highly enhanced than the features present in the image of the left. Also, you can see that the size of the image is reduced. Okay, so we saw.
So can you see, guys, this is input image, which is convolved by using a vertical edge filter, vertical edge detector, which we have discussed earlier. Now we are convolving, we are using max pooling layer to reduce the size little bit, to reduce the computational cost. Plus, by using maximum pooling, like selecting a maximum pixel values from that particular filter size, and selecting only maximum size, by we are using a maximum pooling, which will help you out to enhance, indirectly enhance the vertical edges. Can you see this? Here we are not able to see it properly, but here it is enhanced. So the features are enhanced as well. Enhances the features by using max pooling.
Why do we need max pooling layer? Now let's see, where do we need max pooling layer? Max pooling layer is always applied after the convolutional layer. So once we extract the features, we can use max pooling layers to reduce the size of the output image from the convolutional layer and to enhance the features. And here by convolutional layer, I just mean performing the convolutional operation using many filters. Let's say if we are using 5 number of filters in one convolutional layer, then we know that we will generate 5 number of output images. Thus, after performing the max pooling operation, we will again get the same number, means 5 number of images in the output of the max pooling layer as well. Now, in an entire convolutional neural network, we will use many number of convolutional layers and max pooling layers. Here, there is a small side note. It is not always necessary to use max pooling layer after every convolutional layer. You may just use convolutional layers and can also skip max pooling layers, or just use fewer number of max pooling layers than the number of convolutional layers. The reason for that is that we saw that the max pooling layer reduces the size of the image. But we might not want to reduce the size too much if we are using a very big convolutional neural network. All this will be clearer once we learn the convolutional neural network architecture in the upcoming videos. But it is for sure that the use of the max pooling will improve the performance of the model and can be very powerful. Another thing to note here is that there are no parameters involved while performing the max pooling operation. So this is just a simple transformation operation, and thus no training is required in it as there are no parameters to learn. Now there can be other types of pooling layers as well. For example, there can be average pooling, in which we will take the average of the values in that one filter. For example, here 3.5 is the average of all these four values in one window of that filter. So now let's summarize everything we have learned so far. Max pooling reduces the size of the image while preserving the features, and thus reducing the computational cost or the number of operations required to process the image. And also it enhances the detected features from the image. It is applied only after the convolutional layers, and there are no parameters involved in it, thus no training is required, and the number of channels or images in the output will be same as the input. For example, previously we saw that if the output of the convolutional layers is 5 image, then the output after performing the max pooling operation on these 5 image will also be 5. So if you found this video helpful, then make sure to hit the like button and share it among your friends. This will be a great help to them as well as to me. And we will continue our discussion on the convolutional neural network, and in the upcoming video.
Right. So this is your pooling, guys. Pooling can be max pooling, pooling can be average pooling, pooling can be, there are several types of pooling. We'll discuss that. But I hope you guys uh, got the clarity about why pooling is needed. Let's discuss now. What does pooling does is, pooling tries to figure out whether a particular region in the image has the feature we are interested in or not. It essentially looks at larger region, right? Having multiple patches. Larger region having multiple patches of the image and captures what? An aggregate statistics, that is maximum, average, etc. of each region. In other words, it makes the network invariant to local transformation. Correct? The two most popular aggregate functions are two most popular aggregate functions are functions used in pooling are max and average, right? So we have max pooling. So if any one of the patches says something strongly about the presence of a certain feature, then the pooling layer counts that feature as detected. Correct? Then we have average pooling. If one patch says something very firmly, but the other ones disagree, then the pooling layer takes the average to find out. Right? If one patch says something strongly about the presence of certain feature, then pooling layer counts the that feature as detected. Right? If one patch says something very firmly, but the other one disagree, then the pooling layer takes the average to find out. Right? There are multiple pooling layers. So that is what we have, guys. Suppose if you have a layer like this, 1, 2, 3, 4, 1, 2, 3, 4. This is your input size, suppose. Right? 1, 2, 5, 23, 7, 5, 3, 11, 18, 21, 9, 2, 4, 3, 56, 0. And here we have 1, 2, 3, 4, this one. So it is 7, 23, 21, 56. And this is max pooling. Correct? So for this, suppose 2 by 2 filter, right? So for this, 7 is maximum. For this, 23 is maximum. For this, 21 is maximum. For this, 56 is maximum. Correct? So in the above figure, you can observe that only width and height of the input reduces. Only width and height is reduces. Let's extend this pooling to multiple feature maps. Suppose you have two feature maps, one over another like this. This one and this one. Suppose like this. Correct? And you're applying a max pooling to that. You're applying max pooling to that. So this is your pooling operation. This is also your pooling operation. This is max pooling with stride 2. This is also max pooling with stride 2. Correct? And at the last, you'll be having this one. So suppose, let me color this out now. Suppose this is yellow. So this will be yellow. And suppose this is black. So this will be black. Then here it will happen the max pooling, like suppose we have numbers like this 1 2 3 4. So max pooling, here also max pooling, and then finally only height and width decreases like that. So this is multiple layers, guys, multiple layers. I'll share this figure, don't worry. So pooling, if you observe, pooling reduces the feature map, right? It reduces the size and width and height of each feature map, but the number of feature maps remains same, right? Here, if you have one feature map, only one feature map. If you have two feature maps, two feature maps, so output may be two feature maps. Like here also will be having two feature maps. Correct. Now that is what we have. It reduces the size, but it reduces the size. ठीक है. Pooling operates on each feature map independently. It reduces the size, that is width, and height of each feature map, but the number of feature maps remains constant. Correct? And pooling has the advantage of making the representation more compact by reducing the spatial size, that is height and width, correct, of the feature maps, thereby reducing the number of parameters to be learned, thereby reducing the parameters to be learned, correct. And on the other hand, it also loses a lot of information. That is also possible. But it also loses a lot of information, which is often considered potential disadvantage. Having said that, pooling has empirically proven to improve the performance of deep deep CNN, right? It also loses a lot of information which often considered a potential disadvantage, but pooling has empirically proven to improve the performance of the most deep CNN, right? So can we design an architecture, a network without pooling? Can we do that? So we can do that, but it is computationally expensive, right? It is known as capsule network, guys. Capsule networks. What is the capsule networks? They were designed to address some of this potential drawbacks. Potential drawbacks of what? Of the conventional CNN architecture, right? So the paper on the capsule networks, I'll be sharing that. You can read about that. It is out of your syllabus anyway. So dynamic routing between capsules. We have on paper. This one. Yes, this one only. You can read this, guys, to get an idea about this. This paper is free, I think. View PDF. It is free. This one only. Geoffrey Hinton. Do you know this guy? Even though it's silly question, but you should know this. Do you know this guy? Guys, do you know Geoffrey Hinton? Recently, he has won Nobel Prize for Physics, na? Nobody knows this. He's the father of AI. Godfather, not father. Godfather of AI. So basically, he recently won a Nobel Prize for, can you say this, for physics? So if you are, studying AI, ML, deep learning, neural networks, you should know these people out there, and you should read about them, how they did this, and what is their research is all about. Correct? So it is published by him only. He is associated with Google. Read about this guy. It's interesting. Capsule networks. And I'm sharing this link. Just go through this. Let me know if you have any questions. Now it's time to put all the components that we have studied together, which forms your fully connected layer. So you watch this. I'll be adding a quick heading over here. Fully connected layers, or let's call it as putting the components together. Correct? Putting the components together. Let's call it as this. Let's call it as 15. And cheek. Now, this is what we have. Let's watch this. You'll understand it.
So far in this CNN series, we have seen that the convolutional layers extract the features from the images. And we use many such layers to extract appropriate features from the images. But it just extracts the features from the images. So how do we classify these features to a particular label or a category? And how do we make our model to learn to associate particular features with a label? For example, after some combination of convolutional layers and max pooling layers, we might have a features of face extracted from an image. Now, what layer do we use to classify the features? The answer to this question is fully connected layers. And in this video, we will see what is fully connected layers, why do we use it, and where do we apply them. And if you have been following my content for a while, then make sure to hit the red subscribe button and also do like this video if you find it helpful and share it among your friends. For this video, let's see what are fully connected layers. Fully connected layers is nothing but a dense network of neurons and connection between every two neurons. It is just as our simple neural network or artificial neural network that we have seen before. We use fully connected layers to classify image to a particular category after we have extracted the features from the image using convolutional layers and max pooling layers. Let's say after passing through the combination of many convolutional layers and the max pooling layers, we extract the features from the images, and at the end we obtain these four images. Now these four images will then be passed to the fully connected layers. And the way we do it is by flattening these images into a one-dimensional vector. So now these 4 images are now flattened into a single one-dimensional array. And now this flattened array will be used as an input to the fully connected layers. This one single layer is called one fully connected layer. It is called fully connected layer because every single neuron of that layer is connected to all the neurons of the previous layer and to the next fully connected layer. So here we can say that we have 3 fully connected layers, and the final fully connected layer or the output fully connected layer will have the same number of neurons as the number of categories we have. For example, if we are making a model to identify 4 kinds of objects such as apple, orange, banana and grapes, then the number of neurons in this fully connected layer will be equal to 4. And for this layer, we will use softmax activation function to classify the image into a particular category. If we had been doing the binary classification, then the number of neuron in this layer would have been just 1, and we would have used sigmoid activation function. Now, the connection between the neurons are also called weights or the W parameters. And these weights are trainable parameters that our model needs to learn. Thus, you can say that the fully connected layers are also responsible for not just classifying the image into a particular category, but also to learn to associate features to a particular category. For example, to associate the features of a face to a particular label human. Thus, fully connected layers are an essential part of the convolutional neural network architecture. So far we have seen that the fully connected layers are the dense network of neurons, and every single neuron is connected to every other neuron from the previous layer and the next layer. Fully connected layers are applied after all the convolutional and max pooling layers, and the purpose of the fully connected layers is to classify the image into a particular category and to associate features to a particular label. Now this was about the fully connected layers, and now we have learned all the components that are required to create a forward propagation in the convolutional neural network. So in the next video, we will see the entire convolutional neural network architecture. You can go to the next video by clicking somewhere in the right or the left side of this video. So far in the CNN series, the entire playlist, does it look like? We have already seen the convolution operation and we have seen how does it work. Let's say if we perform the convolution operation on this image of the dog and we get now the values in this image needs to be scaled properly. So what do we do is that we add a bias and pass it to a non-linear function. This non-linear function can be 10h or ReLU, but most commonly ReLU is only used. And afterwards we will get this image in the output whose size will be same as this image. This entire unit, which consists of one applying the convolution operation and the other applying the non-linear activation function, is a convolutional layer. So whenever I talk about the convolutional layer, it means that we are applying the convolution operation using a filter, and then we are adding a bias to the output and passing it to the non-linear activation function. And if we use multiple filters, then the bias here will be changed and we will get these multiple outputs. So in short, I will represent this. this thing with the help of this, where here this 4 means that we are using 4 filters, where the filter size is this. We are applying the convolutional layer and we are getting the 4 channeled output. So using this, let's see how the convolutional neural network architecture looks like. First, we have an input image. Let's say this image is of the size 32 cross 32 cross 3. Here 3 represents that we are using an RGB image or a colored image which will have red, green and blue channels. First, we will convolve this image with a particular filter size. Let's say the filter size is given by 5 cross 5 cross 3, where this 3 matches with this 3, and we are using a stride of 1 and we are using 4 filters. Thus the output will be 28 cross 28 cross 4. This 28 here is nothing but n minus f plus 1, which is equal to 32 minus 5 plus 1, which is equal to 28. And as we are using 4 number of filters, we will get this 4-dimensional output. Now, after convolving this image, we pass this to a max pooling layer. So let's say we are using a max pooling with the filter size 2 cross 2 and stride true. Thus the dimension will become half. So here 28 by 28 will become by 14 by 14 and the number of channels will remain the same. Notice how here I am using 1 for convolutional layer and max pooling layer. Traditionally in CNN, the combination of both the convolutional layer and the max pooling layer is considered as one layer. Thus we can say that this is our first convolutional layer and this is the first max pooling layer, and together it is the first layer of our CNN. Now this output will again be passed to a convolutional layer, which will be a conv2 layer, and here we can use any other different filter size, but notice here that this 4 must match with this 4. And let's say here we are using 8 filters, thus the output here will have 8 channels. And again this is passed to the max pooling layer, and we will get the output of this size. And this layer will be considered as the second layer of our CNN. Thus this is the second convolution layer and second max pooling layer. Now we can continue repeating these convolutional layers and max pooling layers as many times as we want, and it depends on the type of application. If we are performing a very complicated application, then we might need a complex or a large convolutional architecture. But if we are to make a simple application, then a simple architecture will also do. We can only keep few number of convolutional and max pooling layers. Also, there is another thing to note here, that is we can completely skip this max pooling operation or max pooling layer if we are building a big CNN architecture, because the max pooling layer will reduce the size of the image that we are dealing with, and we might not want to reduce the size too much. But for a small architecture, the using of max pooling will definitely enhance the performance. Now once we are done with all the convolutional layers and max pooling layers, then it's time to add our fully connected layers. But before we can apply fully connected layers, we need to flatten this final image output. So the 6 cross 6 cross 8 will be flattened into a only one dimensional vector, which is 6 by 6 by 8, which is nothing but 288 units in one vector. Now once we have flattened it, we can now connect this with a fully connected layer. This will be represented by FC3, meaning that this is the third layer of our CNN architecture. Let's say we keep the 120 neurons in this layer. Then these 120 neurons will be connected with every single neurons of this vector. The number of weight parameters here will be 288 cross 120. Now we can add multiple fully connected layers here as much as we want, but now we can add multiple fully connected layers here as much as we want, but it is to note here that adding fully connected layer highly increases the amount of parameters that we need to deal with. Then in the final layer, we will be applying the sigmoid or softmax activation function, depends on the type of application we are making. For example, if we are performing the binary classification, then we will be using sigmoid, or if we are performing multi-class classification, then we will be using softmax activation function. This final layer can be also called as a sigmoid layer or softmax layer or FC4 layer. And for softmax, it is necessary to note here that the number of neurons in this layer should be equal to the number of output categories. This final layer will give us our ypred. This ypred here is nothing but the prediction of the category of our image. But before we can predict anything, we need to train our model, right? Otherwise, how will these parameters know what values to take? So now what happens is that we use this ypred and use it to calculate the cost function. Now this cost function will tell us the amount of error that the model is getting while making predictions. Now the question is which cost function to use. The answer is that if we are performing binary classification, then we will be using binary cross entropy cost function. And if we are performing multi-class classification, then we can use categorical cross entropy cross function. The discussion about the type of cost function to use have already been covered by me in the neural network playlist. So if you want to check that out, you can find its link by clicking on the upper I button, or you can also find the link down in the description box. And again, our job is to minimize this cost function so that we can train our model and make it more accurate. So how do we do the training? The answer is by using our same old backpropagation algorithm or the backpropagation technique that we used in our ANN or the artificial neural network or the simple or normal neural network. And we can use here any backpropagation algorithm, for example, stochastic gradient descent or or gradient descent with Adam or gradient descent with momentum, etc. So this is how the complete architecture of the CNN looks like. If we sum this architecture, then we can see
So this is how your architecture would be. This is what we are going to build now in the other half of the session.
the difference
Correct?
between the ANN and the
This is
CNN.
the difference between ANN and CNN, guys. Just have a look at this.
Here from ANN, I just mean the traditional or the simple neural network that we use. It is also called as an artificial neural network. In ANN, we use this dense network of these neurons, and these layers can also be represented with fully connected layers. So in short, in the ANN, we use many fully connected layers and we have a dense network of neurons, and thus the total number of parameters are extremely high. But we can reduce the number of parameters by using these convolution layers and max pooling layers, because these layers only take handful number of parameters. There is another side note here. These images that we get in the output after the convolutional layers and the max pooling layers are sometimes also called as a feature map. So these feature map hold the
So these are known as feature maps, the image that we get after the convolution, after the pooling, after the convolution.
feature patterns of the input dataset or the input images. And once we have this YPRED, from here on it's the same both in ANN in CNN, that we apply a cost function and the backpropagation algorithm. And regarding the implementation of these backpropagation algorithm in CNN, the backpropagation in CNN is actually very complicated, because here we also need to calculate the del cost by del W. But the challenge here is that the W parameters are actually inside the filters that are used for the convolutional operation. Thus, calculating this del cost by del W and applying the gradient descent becomes very complicated in CNN. So to make this job easy, what we do is that we use something called as a TensorFlow framework in Python. So what does this framework do is that it makes our implementation quick and easy. We don't need to deal with the details and the nitty-gritty of the complex technique, but we can just mention the name. For example, we can just mention the name of the cost function that we want to use, or the name of the backpropagation technique we want to use, for example, Adam or momentum or stochastic gradient descent, and the TensorFlow will automatically implement it for us. The advantage of this is that, let's say you make a convolutional neural network and you found out that the accuracy is not pretty good. Then you might want to add some layers or remove some layers or modify the network. And whenever you modify the layers, you will also need to do the same modification in the backpropagation as well. And making the modification in the backpropagation will be complicated, and there are chances that it will lead to errors. Thus, all this will be very complex and very time consuming, and we won't be able to focus properly on the architecture design. But using TensorFlow, we can just mention the type of layer that we want to use. For example, we will just mention conv layer and pass the parameters like stride, padding, etc. Then we can just mention that we want to use max pooling layer. Then we will pass the parameters. Then again, we will write that we want to use max convolutional layers, and so on. Thus, building the architecture in the TensorFlow is very simple, where we just have to specify what we want to use and where we want to use it, and the implementation is taken care by the TensorFlow. And if we change the layers, all the modifications in the backpropagation will automatically be done. Thus, that's it for this video. If you found this valuable, then please hit the like button. Also share it among your friends so that they can also be benefited from this video. And we have learned all the basic theory behind.
So that is your fully connected layer, guys. Yeah, that's what we have. Then in putting all the components together, that's what we have seen. Like um, till now, you have seen convolution operation, convolutions. You have seen feature maps. You have seen pooling layers. Correct. Let's now quickly summarize and put them together. Put them together, right? For example, to summarize, uh, typical CNN layer, or we call it as unit. It involves the following two components in sequence. We start with an original image and do convolutions using multiple filters to get multiple feature maps. Correct. Second is a pooling layer takes the statistical aggregate of the feature maps. The pooling layer takes statistical aggregate of the feature maps. Third one is yeah. Correct. Now, typically a deep CNN have multiple such CNN unit. A deep CNNs have multiple such CNN units. That is feature map pooling pairs arranged sequentially. Right. Now, to summarize a typical CNN, it has following sequence of CNN layers. First is we have an input image, which is convolved using multiple feature maps. Then each feature map of size C by C is pooled to generate a C by 2 of a C by 2 output for a standard 2 by 2 pooling. Then third is the above pattern is called a CNN layer or unit, and multiple such CNN layers are stacked on top of one another to create deep CNN networks. And note that pooling reduces only the height and width of a feature map, not the depth. That is number of channels. For example, if you have M feature maps of size C by C, and pooling operation will reduce M output. So if you have M feature maps, each of size C by C, so feature maps will not reduce. Feature map will not be reduced. Pooling operation, if you perform on this, so it will produce M output only. M feature maps, so M outputs, but size will be C by 2 and C by 2. Let's say size is reduced. So height and width wise, it is reduced. Correct. So that is your summarization of entire CNN architecture, guys. So in this session, you learned basic of convolutional neural networks and their common applications. Basics. Their common applications in computer vision, such as image classifications and object detection. You also learned that CNN are not limited to images, but they can also extend it to videos. Videos are nothing but your sequence of images at different timestamps, right? To design CNN, you many to design a CNN, many observations such as animal visual system, annual visual systems, such as retinal neurons, look at its own receptive field. Some neurons respond proportionally to the summation of overexcitation representatory region, and the images are perceived in a hierarchical manner. You learn that images are naturally represented in the form of arrays. Grayscale image. Grayscale image have a single channel. Have a single channel. While color image have three channels. RGB. Correct? Between it, color intensity 0 to 255. Right? You also saw that we use specialized filters or known as kernels that can be designed to extract specific features from images such as vertical edges, horizontal edges, right? A filter convolves an image and extract features from each patch. Multiple filters are used. Multiple filters are used to extract different features from image, and convolutions can be done using various strides and paddings. Various strides and paddings, right? So the formula to calculate output shape after convolution is given by, I have already given the formula, n plus 2p minus k divided by s plus 1 by this n plus 2p minus k divided by s plus 1, right? So n represents image size, k represents filter, p represents padding, s represents stride. Correct? The filters are learned during training, during back propagation, which we have seen in today's session. So I will not revise what we have discussed in today's session, right? Today's session, you can have a summary over here. So that is your deep convolution neural networks, guys. Now we are going to study the uh, how do we build CNN using uh, how do we build and train CNN using Python plus Keras plus GPUs. We'll see that. Correct? Getting this, guys? Understanding this, guys? This one? Okay, perfect. Now let's have a break for 15 minutes. We'll start somewhere around 11 o'clock. You'll be having a quiz now, guys. A Kahoot.
Hi everyone, I hope I'm audible. So we'll have a quick count now. I'll be sharing the link. Kindly join fast. Thank you everyone for joining. Deepul, you can take care of the session.
All right, guys. All right. Let's see this. Let's see the practical implementation now. So what I'll be doing is, first of all, let me share my screen. Here, let us create day number. $39, correct? Day 39, 22nd, Feb, and here we will be creating new collab notebook. This, right? Now, we'll be building a basic CNN, guys, basic with no variation. So let's call it as building a basic CNN on the MNIST data. If you want, you can do simultaneously with me. To this notes from the spreadsheet. Yes, because you made changes now on machine learning, Excel now, LLM wrongling. It's a copy of it, but change. Correct, correct, correct. It's not reflecting. I know that. I'll just copy this and make changes over here. This one. Right here, let me just create a new notebook. Sorry, not notebook. 22nd page. Right, and I'll be just pasting it over here. Correct? Or instead of that, paste it from start. So it will be there now on your sheet. All right. So what we are going to do, guys, is in this notebook, we will build simple CNN based architecture to classify the 10 digits, that is 0 to 9, of the MNIST data set, right? The objective here of this notebook is to become familiar with the process of building CNNs in Kernels. Right now, we will go through the following steps. One, importing libraries and the datasets. Second is data preparation, train, test, split, and we'll be specifying the shape of the input data, etc. Third is we'll be building and understanding the CNN architecture. Fourth one is we are going to fit and evaluate the model. Now let's dive in. Right. So just give me a minute, please. right? So first of all, we'll import the necessary libraries and the dataset. Let's load the required libraries from Keras. We need to import two main components, right? First component is sequential. From keras.model, we'll import sequential. It is the Keras abstraction for creating models with a stack of layers. That is, multi-layer perceptron has multiple hidden layers, and CNNs have convolutional layers, etc. Correct. Second one is various types of layers from keras.layers. These layers are added one after the other. These layers are added one after the other to the sequential model. To the sequential model. And the Keras backend is needed for Keras to know that you are using TensorFlow, not Piano at the backend. Right? So Keras backend is needed because for Keras to know that you are using TensorFlow, not Theano. Theano is another architecture, not architecture, library. Python library that helps mathematical expression. But we are not using that. We are using your TensorFlow. So import NumPy as NP, import random, import TensorFlow as EF, from TensorFlow dot keras dot datasets. We are going to import MNIST from TensorFlow. So it's a pre-built dataset, guys. It's already built in Keras. Now from TensorFlow dot keras, we're going to import sequential from TensorFlow dot keras dot layers. We're going to import dense, drop out, flatten, conv2d, and max pooling. Right? So these are the different layers that we are going to use. Dense, drop out, flatten, conv2d, and max pooling. Done. Now let us load the MNIST dataset from keras.datasets. And the download may take a few minutes. So I'm going to load the dataset into train and test sets. So x underscore train, y underscore train, x underscore test, y underscore test is equals to MNIST dot load underscore data open close bracket. Right? I'm going to print train underscore data, train data. I'm going to print x underscore train dot shape. I'm going to print y underscore train dot shape to print slash n test data. Then I'm going to print x underscore test dot shape and print y underscore test dot shape. Correct? Now, okay, okay. X train spelling is wrong. Why there is a warning for TensorFlow.keras? Where is the warning? This one. No, it's just a could not be resolved. It's a report missing imports. No, it's not needed. Like you can do like this, or you can do from TensorFlow import keras, and then you can write down keras.datasets. But I'm directly using TensorFlow. No? See, it is suggesting us to use TF because we already have imported TensorFlow as TF. So it's your choice, but let's not focus on that. Unless and until we are not getting any error, it is fine. Correct? So we have somewhere around 60,000 training dataset and 10,000 testing images of size 28 by 28. And note that images are grayscale, thus are stored in 2D arrays, right? Images are grayscale. So we have 60,000 training and 10,000 test images, each of size 28 by 28. Note that the images are grayscale and thus are stored as 2D arrays, right? Also, let's sample only 20K images for training just to speed up the training a bit, correct? Now I'm going to sample only 20K images for training. We have to sample only 20K images for training. So idx is equals to np.random integer x underscore train dot shape of 0 comma size is equals to 20,000. We are going to sample 20K indices from 0 to 60,000. X underscore train is equals to x underscore train idx comma this y underscore train is equals to y underscore train of idx. Going to print x underscore train dot shape. I'm going to print y underscore train dot shape. Correct? Now I'm going to prepare a data. Data preparation. So let's prepare the data set for feeding to the network, and we will do the following 3 main steps, right? 2.1, we are going to reshape the data. So first, let's understand the shape in which the network expects the training data. Since we have 20,000 training samples, each of size 28 by 28 by 1, and the training data x underscore train needs to be of the shape 20,000 comma 28 comma 28 comma 1. If the images were colored, the shape would have been 20,000. If it is color, then it would have been 28 by 28 by 3. Correct? Now, further, each of the 20,000 images have 0 to 9 label. So y underscore train needs to be of shape 20,000 comma 10, because 0 to 9 are 10 classes, where each image label is where each image label is represented as a 10b1 hot encoded vector, right? And the shapes of x underscore test and y underscore test will be the same as that of x underscore train and y underscore train respectively. Correct? So this is your reshaping the data. Now, after reshaping, we should go with 2.2, that is rescaling, that is normalization. So the value of each pixel is between 0 to 255. So we will rescale each pixel by dividing 255 by dividing by 255, so that the range becomes 0 to 1, and we will recollect why normalization is important for training neural networks, right? So 2.3 is converting input data type integer to float. So the pixels are originally stored as type integer, but it is advisable to feed data as float. This is not really compulsory, but advisable, and you can read why conversion from integer to float is helpful here. So why normalization is important for training neural network, guys? You can read an article for that. I'm just giving you guys an article. Anyway, we have seen this thing. Why normalization is required, or why do we need to normalize the images before we put them into CNN. There's one website called Stack Exchange. This one, correct? You can read this article, guys. I'm just adding it over here. Here, correct? And there's one more thing. Why converting this? What we can say? Why converting input data type to integer is needed? For that, I'll be sharing one more link, which is for Stack Exchange only. Neural network data type conversion from float 20. This one. You can read this, why data type conversion is needed. Correct. So this is also something which is interesting. Give it a try. Right. Now, after converting to this, guys, we'll specify input dimensions of each image underscore rows, comma, image underscore columns is equals to 28 by 28. Input underscore shape is equals to image underscore rows, comma, image underscore columns, comma 1, and batch size, number of classes, epochs, batch underscore size is equals to 128, number underscore classes is equals to 10, epochs is equals to 12. Let's now reshape this. Let's now reshape the array underscore train from shape 20,000 comma 28 comma 28 to 20,000 comma 28 comma 28 1 analogously for x underscore test. Right, so I'll reshape x underscore train and x underscore test. X underscore train is equals to x underscore train dot reshape x underscore train dot shape of 0 comma image underscore rows comma image underscore columns comma 1 x underscore test is equals to x underscore test dot reshape x underscore test dot shape of 0 comma image underscore rows comma image underscore columns 1. And I'm going to print this x underscore train comma shape. Then I'm going to print this x underscore test dot shape. Right now, let us reshape y underscore train from 20,000 comma 1 to 20,000 comma 10, because we have 10 classes, right? So this can be conveniently done using the Keras utils module. Correct? So Keras utility module converts that particular into converting class labels, that is from digits to one hot encoded vectors. To one hot encoded vectors. If I write on y underscore train tf dot keras dot utils dot to underscore categorical y underscore train number underscore classes y test equals to tf dot keras dot utils to categorical y test to number classes. What is the number of classes, guys? We have 10 number of classes. So I'm converting this shape from 20,001 to 20,010. Simple. Correct. So let me write down over here. Finally, let's convert the data type of x underscore train and x underscore test from integer to float and normalize the images. Correct. So originally the pixels are stored as integers. Originally the pixels are stored as integers. Now I'm going to converting integer to float by using this x train equals to x underscore train dot ace type float 32 x underscore test is equals to x underscore test dot reshape float 32 normalize x underscore train comma equals to 55 x underscore test divided by equals to 255. This is happening. I'm not able to do. Not reshape, guys. It should be AS type. My bad. So converting this integer into float, right? And doing normalization. Now this is done. Data preparation is done. Let's go with the third step of building the model. So let's now build the CNN architecture for the MNIST dataset. We do not need to build a very sophisticated CNN. Do not need to build a very sophisticated CNN. A simple, shallowish CNN would suffice, right? So we will build a network with two convolutional layers having 32 and 64 filters respectively, followed by a max pooling layer, and then flatten the output of the pooling layer to give a long vector, and then add a fully connected dense layer with 128 neurons, and finally add a softmax layer with 10 neurons, right? So the generic way to build a model in Keras is to instantiate a sequential model and keep adding Keras dot layers with we will also use some dropouts. Right? I think this is a single line. So the generic way to build a model in Keras is to instantiate a sequential model and keep adding Keras.layers to it. We'll also use some dropouts on there. So I'm creating a model. Model is equals to sequential, open close bracket. A Keras convolutional layer is called conv2d. If you write in help conv2d, note that the first layer needs to be told the input shape explicitly, and the first convolution layer, that is model.add con2d 32 comma kernel size equals to 3 comma 3 comma activation is equals to value comma input underscore shape is equals to input underscore shape. So basically input underscore or input shape is equals to image underscore rows comma image underscore columns comma 1, and then we'll be having second layer, a second convolution layer. So model.add con2d 64 comma kernel underscore size is equals to 3 by 3 comma activation is equals to value model.add max pooling 2d size is equals to 2 comma 2 model.add going to add a dropout 0.25. Then let's flatten this and put a fully connected layer model.add flatten open close bracket model.add dense 128 activation is equals to value. This is a fully connected layer, guys. And then we'll be adding a dropout after this fully connected layer 0.5. And let's add softmax now. Softmax layer. So I'll be adding model.add dense layer, number of classes, activation is equals to softmax because we have multi-class classification. And last but not the least, I want model summary. I'll add a model dot summary. Correct. This is what we have, guys. This is what we have. A model summary 26, 26, 32. Total number of parameters are this. Trainable parameters are this. You can use this. I told you how do we calculate trainable parameters. I'm going to give you summary over here. Don't worry. But before that, sorry, after that, before summary, not after, let's fit the model. So fitting and evaluating the model over here. Correct. So let us now compile and train the model. Let us now compile and train the model. So usually cross entropy loss, we choose any optimizer such as Adam, RMS, prop, etc. And metric is accuracy, right? Because it's a classification, we should use a accuracy metric. So loss is equals to tf dot keras dot losses dot categorical underscore cross entropy comma optimizer is equals to tf dot keras dot optimizer dot add a delta open and close bracket comma matrix is equals to accuracy and close this. Optimizer, correct. Now I'm going to build the model and this should take around 10 to 15 minutes when run locally on a Windows or a Mac or PC. So model.fit. Now as the trainable parameters are more than 1 lakh, 11 lakh, right? 11 lakh trainable parameters. So it will take 15 minutes, guys, to fit this. At least 10 to 15 minutes. So batch underscore size is equals to the batch size that we have, comma, epochs is equals to epochs, comma, verbose is equals to 1, comma, validation underscore data is equals to x underscore test, comma, y underscore test. Right? Now I'm going to evaluate comma is missing, na? Correct. Comma is missing. Now it's time to evaluate the model on test data. File return model.evaluate on x underscore test, comma y underscore test. And then I'm going to print the model dot metrics underscore names. Simple. So let's wait for this, guys, because as I told, it is the total trainable parameters are 11 lakh. What is verbose? It's a parameter, verbose. You might have studied this in decision tree as well. Verbose parameter. It's a parameter in deep learning. It is to set logging level during model training and validation process. Verbose argument can take one of three integer. So it's a hyperparameter. Optional argument in various methods, including fit and evaluate. It is to set logging level. Silent mode, no output during training. Verbose equals to 1 means progress bar mode. Okay. So this is verbose, guys. Progress bar mode. If I write on 0, means I'll not able to see what is happening like this progress bar. Correct? And verbose equals to means 1 line per epoch. Show the summary of training and validation metrics after each epoch. After each epoch, it will show summary of the training and validation. So if I write verbose equals to 1, it's a progress bar mode, this one. Displays the progress bar with training and validation metrics. It is displaying the progress bar with this. It's a hyperparameter. Good. It's good that you have asked this question. So you can choose one, you can choose two. That's not a problem. It's a hyperparameter. You can choose any hyperparameter out there. Correct? Okay, let's wait for this, guys. Let us wait for this. Then we'll be printing model dot evaluation metrics underscore names. That is what we have. So final loss and final accuracy will get over here. Correct? Let me pause this. Or instead of that, let's copy this. Let us delete this. Let us add a code cell. Anything just pasted over here. Okay. Let's wait for this now. Waiting for this output. I think 10 epochs are done, no? Let's wait for 11th and 12th. Does every image data takes more time like this? If you are feeding it for let's say if trainable parameters are this much, can you just imagine it is training on near about 12 lakhs parameter, 12 lakhs parameter, right? So 12 lakhs parameters are being trained, and it is using your local GPU. If you buy some, if you purchase some credits to this, change runtime, this one. If you buy this, no, sorry, not this, this one, purchase additional compute units, then it will save your time of computation, but it is coming at the cost of this, right? It is good, you can try this. If you're working in the industry, they purchase some computational units like this, or they work nowadays. This is what in a trend, right? If you see Nvidia GPUs or any GPUs out there, why Nvidia stock price multiplied. If you see in this trend, not now it is very poor because of the DeepSeek model. But if you see from the evolution of this computation units or GPU, it has rise like this. Can you see 10 November 2023, 5 Jan 2024, it was 49, rise to 94, again rise to 131, from 49 to 134 in just 6 months span. Can you just see June and Jan? 6 months, just 6 months. It was 149, something like that. 131. So from I think 49 to 131. Just calculate the 131 minus 49 divided by 49. It will be, sorry, 49. And if you divide this with 49, it is 167% profit just in 6 months. And then it rose to 147. So this was the highest time in, and then in the last month itself, because of uh, the rise of this deep seek model, it it was down to, in the last month itself, if you see from this 147 to directly on 118 within just how many days? 4 days. Can you see? Because of DeepSeek. And now again poor, and then now it is coming to back to this position. So these people are now, playing their games, or earning money by selling this GPU unit. For earlier, this was just for for games purpose or for coding purpose, but now it has evolved. The trend has evolved in such a way that to train your uh, large language models or AI models, you are um, what we can see. You are using this GPU. You are using these GPUs, correct? So this is what we have. So here also, it is you can buy this credit basically. All right. Okay, then I think this is done, correct? And if I just run this, evaluate and print the model, final accuracy will be, we'll get the final accuracy. So the final loss on the data is 0 point loss, no? Where is that? Where is that? To final loss on the data is test data. Where is the test data? 1.89, and final accuracy is 0.71. Correct? Okay, so I'm just sharing the case study, guys. The summary of this case study. Just let me convolution neural networks. This one, not industry application. Convolution neural networks. This one. Okay, I'm just giving you guys a summary so that you can use it. Any doubts in this, guys? Till now, whatever we have discussed, any doubts in this? So this is normal CNN plus MNIST. Building a normal CNN plus MNIST. Now we'll be adding feature map, we'll be adding more layer, we'll be adding L2 dropout, we'll be adding batch normalization. We'll see performances, right? Now we were only building a CNN with MNIST. So that's what the idea is. This is your summary. I'll just copy this and I'm going to paste it over here as your summary. Correct. So it is good practice to spend some time starting at the model summary above and verify the number of parameters. So this is a summary, guys. Chalo. All right, guys. We'll stop here for the day. Today we had a session, extended session, half hour. Then we in next session we'll be adding a dropout, batch normalization, more layers, and feature map update. Right? So this is what we have. We'll stop here for the day. Thank you, everyone, and happy learning. Bye. We did not receive the class link for tomorrow. You'll get it, don't worry. I'll ask them to share. You'll get it. चलो ठीक है guys. All right then. Thank you everyone. Bye.